Okay, so good morning, everyone. Good afternoon, good evening, wherever you may be. Welcome to this week's ARMA Future Leader webinar. It is my great pleasure to welcome my dear friend, Dr. Mateo Acosta. Um, Mateo obtained his PhD from EPFL in 2020 under the supervision of Professor Mateo. He joined Caltech in 2021 first as a postdoctoral fellow and then recently as a research scientist, working on various aspects of geomechanics, both in terms of observational studies and numerical geomechanics. And he's recently told me, and I'm glad he's put it into his bio at the beginning here, that he's going to be joining Virginia Tech as an assistant professor in the Department of Geosciences, starting in January next year. So my utmost congratulations to you on that. Mateo's research spans a broad range of interests in geomechanics and how it pertains to fluids in the subsurface. And he has a wide range of scales. His PhD, as it says, was in experimental rock mechanics, but he sort of transitioned to both the observation and the numerical modeling side of field data. Um, and so we're very excited to have this talk and very excited to hear what you have to show. So please, the floor is yours.
Thank you very much for the kind introduction. And apologies for the delay. There was a problem with the time zone. So yeah, thank you for the invitation. I'm extremely happy to be here. And today I will present you a summary of what I've been doing in the last 10 years or so to try to understand the very tight coupling between fluid flow and geomechanical deformation across a bunch of scales. And I will try to show you how we can try to bridge scales using this approach, always looking at figuring out new ways and figure out ways of improving our use of the subsurface to decarbonize the energy matrix. So as most of you know by now, the using the subsurface to decarbonize the economy has really become an essential task of our days. Not only because of the sheer volume of the space that we can use in the subsurface, but also because of the virtually unlimited resources that we can get from there. So here I am showing schematically a few examples of how we can use the subsurface to decarbonize our economy. We can exploit geothermal energy in its many flavors, and there's very active research trying to figure out how we can use geothermal energy everywhere in the world and how we can increase our power production from geothermal energy. So there is an estimation of a few years ago that if we were able to tap on the 10 first kilometers of the crust, we would be able to supply all the energy needs for humanity for about 200 million years. So that tells you about the virtually unlimited potential that we have for producing clean electricity, being sustainable in baseload electricity from geothermal energy. Here in the middle, I am showing an example of carbon capture and storage, be it in a fluid phase or through mineralization of the carbon through chemical reactions with the host rock. And finally, in the last few years, there's been a very large interest in hydrogen extraction and hydrogen storage. So the idea is that we could, in theory, if we understand well the hydromechanical couplings, we could use subsurface reservoirs to store massive amounts of hydrogen that would replace or complement the use of fossil fuels in our economy. And finally, if you look here a little bit deeper in this example, there seems to be very major stored reserves of hydrogen from natural production that we could tap into, again, if we understand well the process of the hydrogen generation, storage, and extraction. So the common thing about all these applications is that they all involve fluids interacting with host rocks and faults. And so if we want to use the subsurface for the energy transition, we need two things. We need first to understand and control the flow rates that we can get from the subsurface. For example, for geothermal power or natural hydrogen, we would need to maximize the flow rate, right, to produce as much heat as possible in geothermal and as much hydrogen as possible in the natural hydrogen problem. And in the case of gas storage and sequestration, we would need to minimize the flows, right? We would need to minimize the leakage through faults, at the same time trying to control what we can inject into the subsurface. And on the other hand, the other way of the coupling, we would need to understand and control the deformation of the rocks and faults that are surrounding these reservoirs that we can use. And so, for example, in the case of geothermal energy, and actually all the other processes, we would need to control or at least understand how faults are reactivated when we inject fluids into the surface, and therefore try to control induced seismicity. And for the cases of gas extraction and storage, we would also really need to understand how the surface subsides or uplifts in response to these injection and extraction processes, and also how rocks fail, for example, by cyclic loading in the case of seasonal storage of gas, for example. And so this brings me to the two big questions of my research, right, that relates to these geomechanical couplings. The first one is really to try to understand how much fluid we can inject or extract from the subsurface and at which timescales this flow takes place. And on the other hand of the coupling, really I want to understand how much the rock deforms and how fast it deforms, because the time scale of the deformation will really matter in a few seconds during earthquakes to tens or hundreds of years for the long-term subsidence and long-term deformation of the reservoirs, right? And so the approach I've been using is really a multi-scale approach, ranging from a few microns, where I've been trying to understand how the contacts in faults or the contacts between minerals control the deformation of the rocks and faults, to a few centimeters to around a meter at the laboratory scale in simulated processes. And lately, during my postdoc and my current position here at Caltech, I've been looking at real case operations at the reservoir scale. So from a few kilometers to a few hundred, to a few tens of kilometers, where we're really using the data from the field to try to understand these hydrogeomechanical couplings. And so the interesting thing about this approach is that at the smallest scales, we have access to direct quantities such as fluid pressures, more or less everywhere in our samples, the stresses, we can control the temperatures, the geometries of our samples. And so this really allows us to understand the physics of fault slip and fluid transport, or rock deformation and fluid transport. But on the other hand, at the larger scale, we might not have access to those direct quantities, but we are able to understand the potential of operations in terms of how much fluid we can inject or extract from the subsurface. And also we can understand the hazard levels in terms of, say, induced seismicity or surface deformation that can affect infrastructure. And so really what I will try to show you through three examples today is that by linking these scales, we might be able to provide new ways of improving our use of the subsurface for decarbonizing the economy. So this is the outline of my talk today. I will show you two examples of the two-way hydromechanical coupling where we used micron scale physics to understand almost meter scale processes in laboratory samples. First on the effect of deformation on fluid transport, and then on how fluid pressures can control laboratory earthquake propagations. And then in the last part, I will show you how we are trying to bridge the scales between earthquake nucleation processes derived from laboratory friction laws and real cases of induced seismicity, and how these two scales can help understand the other one. So I will start with the effect of deformation on fluid transport. So as many of you probably know, there's been a lot of interest in the shear dilatancy mechanism, which accounts for the fact that a fault is expected to be in a fully mated configuration in its equilibrium state. And when this fault is reactivated in shear, the contacts that form this fault, because a fault is the contact between two rough surfaces, will come out of a fully mated configuration, increasing the pore space, as you can see here in the top schema. And this should allow increasing the hydraulic transport properties of the fault, and so increase the permeability of the fault. And so this mechanism has received a lot of interest and seems to be very important for enhanced geothermal systems, where engineers have proposed to inject fluids at high pressures to reactivate the faults in shear, expecting that this would increase their permeability and create an artificial reservoir where we can inject cold fluids and extract hot fluids more or less anywhere in the world. The operation of this shear dilatancy mechanism needs to be quantified and needs to be very well controlled if we want to take these enhanced geothermal systems to a commercial viability, right? And on the other hand, for problems related to carbon sequestration and hydrogen storage, we again need to understand really well these mechanisms if we want to understand how fluids can leak through faults in response to the injections of gas into subsurface reservoirs, right? So if the shear-induced dilatancy mechanism operates, then the risk of leakage would increase in this type of operations. Now, I wanted to show you an example of a real case enhanced geothermal system stimulation from the work of Dempsey and colleagues in 2015. So this is the Desert Peak EGS stimulation. And what you're seeing in this figure is the injection rate in the first y-axis and the blue points versus time during the stimulation process. In black and in the second y-axis, you can see the reported injectivity, which engineers take as a proxy for the permeability of the reservoir close to the injection well. And so what's happening is that they're ramping up the injection rates, right? As you can see here at about 30 days. The injectivity increases, and then they stop the stimulation at around 65 days, right? And then when they restart the stimulation, ramping up again the injection rates at about 85 days, the injectivity they measure is again very low, and it doesn't stay at the significantly high levels that they had during the first stimulation. And no matter how many times you repeat this process, you don't go back to the really high injectivities that you would want for an enhanced geothermal system. And this has been shown more or less pervasively about many enhanced geothermal systems that have used hydroshear stimulations. And there hasn't been a very successful case that would lead to a very interesting economic viability of this type of projects. And so really what I wanted to show with this is that the shear stimulations don't have the desired effect on creating an artificial reservoir of high permeability. And so to try to understand this, we need to understand where this shear dilatancy mechanism comes from. And so this really comes from the engineering geology literature, where people have been shearing faults at relatively low effective normal stresses and measuring the change in aperture or in fault permeability during these reactivation processes. So what you can see here in panel A, B, and C is the work by Yeo and colleagues in 98. And the maps show the aperture field on an artificial fracture, which has been measured at 0 millimeter shear displacement in panel A, 1 millimeter in panel B, and 2 millimeters in panel C. And you can see that the maps become lighter and lighter, meaning that the apertures are increasing with increasing shear displacement. And so this would reflect in the type of permeability with shear displacement evolution that you can see here in panel D from the work of Lee and Cho, where you can see that indeed increasing the shear displacement increases the fracture permeability by a couple of orders of magnitude, and then until you reach a plateau in terms of permeability. Now you will notice that all these experiments were conducted at normal stresses or effective normal stresses, if you want, lower than 3 megapascals, which is not really representative of the stress state that we get at depth. And so really, the previous example in a real case and these examples are fairly contrasting. And so we need to quantify how much this shear-induced dilatancy mechanism operates and at which stresses it operates. So to do this, we conducted experiments on, these are conventional triaxial experiments on different types of fractures, but this time at effective stresses that are much more representative of what we would get at depth in real reservoirs. So this time the effective stresses range from about 30 to about 70 megapascals, and we conducted two types of experiments. One where we have a vertical fracture here in our rock cylinders that are placed in this conventional triaxial hook cell. And we will be injecting fluids here from the top and subtracting them on the bottom to measure the capacity of the fault to transmit fluids, right? These vertical fracture experiments allow to measure the effect of normal stress on the fracture's permeability. And then we conducted a second set of experiments with an oblique fracture, again, injecting and extracting fluids from that fracture, where we could reactivate these fractures in shear and measure the evolution of the permeability of the fault when we are reactivating them in shear. And so the combination of the two experiments really allowed us to isolate the effect of normal stress and the effect of shear displacement on the fracture's permeability. And so these are the results we got. In panel A, you can see the results of the experimental transmissivity or permeability of the fault, if you want, for the vertical fractures, so on the effect of normal stress only. And the different colors show fractures with different initial roughnesses. So something, I won't go too much into the detail here, but that was very interesting from our study is that we were able to customize the roughness on our fracture surfaces in order to have an extremely reproducible set of experiments, and also to understand the exact effect of roughness on the fluid transport properties on the fault. So what you can see from this plot is that the transmissivities have a near exponential decay in the solid lines with increasing effective normal stress, and that the initial roughness of the fractures really control the magnitude of the fluid transport properties in our fault, right? And so here you can see that if we decrease the effective normal stress on our fractures, we would increase their permeability exponentially. And these at stresses that are very representative of deep reservoirs that we're interested in. Now in panel B, what you're seeing are the results of the transmissivity measurements during shear reactivation experiments in these oblique faults. And so in the full lines, you can see experiments conducted at with different, say, maximum effective normal stresses in different colors. And you can see the evolution of shear stress in the full line versus actual displacement on our samples. So what you see is that during the first stages of loading, we have an elastic loading of our sample where the stresses, both shear and normal stress, increase almost linearly until we reach the strength of our fault. And then the fault is reactivated and slides at almost constant shear stresses during this plateau right here. So what we did is that we stopped the deformation every 0.1 millimeters, and we would measure the transmissivity of our samples at these points. The transmissivity values are reported here in the second y-axis, and you can see that at the beginning, the transmissivity does decrease when we're loading elastically our samples, so when we're increasing both normal and shear stress. But then when we have the shear reactivation of the fracture, the transmissivity does not increase, and it actually it slightly decreases with increasing shear displacement. Later, when we unload our samples right here at the end of the experiment, you can see that the transmissivity is not recovered to the values that we had initially, meaning that we've lost some of the transmissivity due to the shear displacement mechanism, right? And so we understood this process using this conceptual diagram here. You can see in the x-axis an increase in normal stress, and in the y-axis towards the bottom, an increase in shear displacement. So really, what the engineering geology literature has shown is that if we reactivate our fractures at low normal stresses, the contacts in the fold would ride past one another, effectively increasing the aperture field and the transmissivity of the folds and giving rise to the shear dilatancy mechanism. But if we were to shear these fractures at high effective normal stresses, we would rather be breaking through the contacts, and this does not have the desired effect of increasing the aperture field, and the debris or the wear products that are generated from this shearing through the contacts can further block the flow paths and reduce the transmissivity. And so really what we have shown, and I think it's an important conclusion for geoenergy operations, is that the transmissivity increase with shear really depends on the effective normal stress level that is applied on the fractures. And so probably at the very large depths where we are deploying enhanced geothermal systems or carbon capture and storage reservoirs, this mechanism might not operate. And so we really need to be very careful when deploying enhanced geothermal systems that we are able to control the effective stress where we are going to reactivate fractures in shear, because if this effective stress is high, we might not get the desired output from the geothermal system. And on the other hand, for carbon capture and hydrogen storage reservoirs, we would rather want to target formations where the surrounding faults are operating at high normal stress levels in order to avoid potential leakage due to the shear dilatancy mechanism, right? And so by understanding what happens at the contact scale, right, with the contact mechanics that drive the changes in flow paths with effective normal stress and with shear displacement, we are able to understand how to better design enhanced geothermal systems or systems for gas capture and storage at the kilometric scale processes. Okay, so that was the first part on the effect of deformation on fluid transport. And now I will show you the other way of the hydromechanical coupling, where we have studied how the ambient fluid pressure can control laboratory earthquake propagation. And so a little bit of introduction here, since the 1960s, Brace and Byerly showed that earthquake cycles could be approximated by a spring slider mechanism. So the idea here is that your fault is at the contact between this plane and this block, who has an applied normal stress on it, and is connected to a spring of a fixed stiffness and loaded at a constant velocity v right here. The loading at this constant velocity makes that shear stress will develop on the interface, and the friction coefficient of the system is expressed as the ratio of the shear to the effective normal stress, right? And in this type of mechanism, changing effective stress and sorry, changing the pore pressure at fixed effective normal stress shouldn't change the evolution of friction, right? And so this type of mechanism, if the stiffness of the spring is in a given range, would give you this type of evolution of the shear stress with time. So you can see that the shear stress increases almost in a linear elastic manner until we reach the strength of the fault. At this point, we have the nucleation of an earthquake, which drops the stresses, increases the slip on the interface. And then as we keep loading the system at constant velocity, this process repeats again. And so if we are able to approximate earthquakes by this very simple spring slider mechanism, the absolute value of the pore pressure shouldn't matter as long as the effective normal stress is comparable. But this is not what we see in the laboratory. So these are triaxial stick slip experiments. I will get a little bit more into the details of this later, conducted at the same effective stress levels, but with changing fluid pressures. So the red one shows a dry experiment with 0 megapascal per fluid pressure. And you can see that these experiments have a much higher strength, much larger stress drops than experiments conducted with an ambient fluid pressure of 1 megapascal in blue or 25 megapascal in black. And you can also see that changing the value of the pore pressure also drastically changes the stick slip behavior of our faults. And so this shows that just the ambient level of pore fluid pressure, and notwithstanding the effective stress concept, can drastically change the behavior of these laboratory earthquakes. And so the way to understand this is that when slip velocities become high, the friction on the faults will drastically drop. So these are called dynamic weakening mechanisms which allow to drop the friction. And so what I'm showing here is a compilation by Aharonov and Schultz and based in the experiments of Di Toro and colleagues mainly, where you can see the evolution of friction versus slip velocity on a constant sliding velocity fault. And you can see that at low sliding velocities, the friction is high, so the faults are strong. But as soon as we reach velocities of a few centimeters per second, there is going to be a lot of heat that is generated in these faults, and this will allow to drop the friction by activating these dynamic weakening mechanisms. And in this case, because these are mechanisms driven by thermal effects, so by increases in temperature, having or not having a pore fluid pressure will drastically change the heating path and also the mechanisms that can be activated. And so to understand this experiment that I showed you before, this is what we did. We have these granite samples that we put into a triaxial conventional triaxial cell with a lot of sensors on the fault. So we control the roughness of our fault interfaces to have reproducibility in our experiments. And the interesting thing about these experiments is that for the first time in the presence of pore fluid pressures, we were able to deploy many instruments in our sample. So in panel C, what I'm showing is a map that you should imagine wrapped around the sample. So the fault right here takes this S-shaped shape in this map. And we deployed 16 lab seismometers or acoustic emission sensors and one ultra-fast sampling frequency, ultra-high sampling frequency strain gauge that allows us to record the stresses with very short timescales. Again, for the first time, we did this in the presence of pore fluid pressures, and we get these results that I showed you before. So what you're seeing here is the experiments I told you about a couple of slides ago. And these are experiments all performed at 70 megapascal effective confinement, but with different ambient levels of pore fluid pressure. So from here, we compile the static stress drops in our experiments and the co-seismic slips during these laboratory earthquakes. And you can see that reported here in panel B. So you can see that the dry experiments had the largest static stress drops and the largest co-seismic slips. The hyperpressure experiments in black had the shortest co-seismic slips and smallest static stress drops on the order of a couple tens of megapascals. But the low pressure experiments with this strange behavior temporally that you see here had a kind of intermediate behavior with low static stress drops, but very large co-seismic slips on the same order of those recorded in dry conditions. And so to understand this, we looked at what happened during the earthquake, the laboratory earthquake event. So this is the record from the high frequency strain gauge that we were able to trigger using the acoustic emission sensors. And what you see is the near fault shear stress again versus time, but zoomed in really into this laboratory earthquake. And you can see that when we reach the strength of our fault, then the stress goes to a peak. It goes down to a dynamic value or a breakdown value that will define what I call the breakdown or dynamic stress drop here. And then the fault heals a little bit more slowly. You will notice that in these plots, the time is in microseconds compared to seconds in panel A. And so we're really recording at very high sampling frequencies what's happening during the earthquakes. And so if I show you all the records of the dry, low pressure and hyper pressure experiments here in panels B, C, and D respectively, you can see that the dry experiment had a very large dynamic stress drop. The low pressure experiments also had a very large dynamic stress drops, but the hyper pressure experiments didn't. And so this is consistent with the very large co-seismic slips that we record from the low pressure experiments. So this time in the same plot I showed you before, I am putting the dynamic stress drops in full symbols, and you can see that the low pressure experiments and dry experiments had these very large magnitude laboratory earthquakes with very large co-seismic slips. So to try to understand this, we went and looked into the post-mortem surfaces, again, to understand what was happening at the contact scale. And this is what's shown here from scanning electron microscope imaging of these post-mortem surfaces. So panel A shows the initial surfaces that were very reproducible and very well controlled with a fairly homogeneous surface roughness. Panels B and D show the dry and low pressure experiments respectively, B and C, where we recorded these very large magnitude earthquakes. And in these experiments, we were able to find pervasive evidence of melt in the surfaces. So these are these stretch structures in the sense of shear that you can see right here. But in the hyperpressure experiment, there was no evidence of melting whatsoever in the whole sample, meaning that the weakening mechanisms in these experiments were drastically different. So from this, we inferred that the dry and low pressure experiments presented a dynamic weakening mechanism that's called flash heating, where basically the contacts in the fault, because they are holding most of the stress applied to the fault, will have much larger shear stresses than the nominal shear stress applied on the fault. And so as soon as these things start to slide, they will generate a lot of heat because the temperature generation is proportional to the product of shear stress and velocity, right? And so we went ahead and conducted a micromechanical model to account for the interactions between the fluid that was surrounding these contacts and the contacts themselves in terms of their thermal evolution. And so what we did is that we computed the flash temperature, so the maximum transient temperature responsible for weakening, as the difference between a heat source rate, right, basically the product of shear stress and velocity, and the temperature buffering term that accounts for the fluid surrounding the contacts that will be cooling down these contacts. Now, the very interesting thing about our approach is that for the first time, we included the dependence on pressure and temperature of the fluid's thermophysical properties. So their density and specific heat mainly would depend on the pressure temperature path taken by the fluid during this heating process. And so this is what is shown right here. I won't go into the details of the equation, but it's basically what I explained, the difference of a heat source rate and a temperature buffering term. And what you can see here in panel A is the evolution of this flash temperature versus sleep during the contact lifetime of the asperity, right? So these are about 20 microns, which we determine from the microstructural analysis. And you can see the different curves are for different constant sliding velocities. So the higher curves for 1 meter per second, intermediate for 10 centimeters per second, and the lowest for 1 centimeter per second. And again, we conduct the experiment, these models under the same experimental conditions. So for the dry experiments, you can see that the flash temperature when the asperity slides at about 10 centimeters per second can reach about 1,000 Celsius. So the temperature for melting of granite. And in that case, we should have the flash heating mechanism operate as soon as we reach that temperature. The low pore pressure case, so when fluids are at 1 megapascal pore pressure, is shown in blue. And so the flash temperature evolution first so the temperature is first buffered until we reach the vaporization temperature of water at 1 megapascal. And at this point, the fluid loses its heat buffering capacity, and we can reach melting temperatures just like in the dry case. And finally, in high pore pressure conditions, so that about 25 megapascals, you can see that the temperature is buffered during the whole lifetime of the asperity, and the temperature is not able to pass the liquid to supercritical transition temperature at 25 megapascals. And this is due to the fact that that liquid to supercritical transition at high pore pressures is accompanied by a drastical increase of the specific heat of the fluid during that transition. So this is what's shown in panel D. You can see the specific heat in the x-axis and the temperature on the y-axis. And the specific heat increases by more than 2,000% at that pressure during that liquid to supercritical transition. And so the capacity of the fluid to buffer heat from the asperity is drastically increased, and it doesn't allow the flash heating mechanism to kick in. And so really here, I think what I've shown you is that by understanding the fluid thermodynamics and the interaction of heating and cooling of the contacts in the fault, we are able to understand why we have large or small magnitude earthquakes in different conditions of ambient pore pressure. And so the implications of this for enhanced geothermal systems, for example, is that if we are able to maintain high pore fluid pressures in what we want our reservoir to be, we would potentially reduce the magnitudes of the earthquakes because we would play with this heat buffering effect that doesn't allow dynamic weakening mechanism to kick in, and so doesn't allow large magnitude earthquakes. This idea has the additional benefit of increasing the permeability of our reservoir if we are able to maintain high pore fluid pressures, because as I showed you before, the effective normal stress has an exponential effect on the permeability of the faults. And so by increasing pore fluid pressures, we would decrease effective normal stress on our faults, and we would really increase the permeability. Right, so again, I think I've shown you, how understanding the problem at the contact scale helps us understand the laboratory scale processes, and then we have ideas on how to improve our operations at the field scale. Okay, so let me get to my last part. Here I will show you how we've been trying to bridge the scales between laboratory-derived earthquake nucleation laws and induced seismicity, and how they can help understand each other, this time at scales from up to a few tens of kilometers. So to introduce a little bit the problem I will show you we figured out. We need to understand that if we want to forecast induced seismicity, and so if we want to forecast the timing of an earthquake, we need to understand several things. First, where we are in the earthquake cycle, and second, how long it takes for these earthquakes to nucleate. And so what I'm showing here in panel A is our conceptual understanding of one earthquake cycle, where we have the distance along the fault in y-axis and time in the x-axis. And so, and in panel B, you're seeing the evolution of the far field stress applied on this fault versus time synchronized with the top panel. And so our understanding is that during the interseismic period, most of the fault is locked, and there might be just very tiny patches that are slipping, that are contained between these green, yellow lines. So everything that is between the lines will be portions of the fault that are sliding, right? And during this interseismic period in green, we have an almost elastic loading of the fault, as I showed you in the previous experiments, right? Then when we reach the fault strength, we will have the nucleation process of an earthquake that should have a finite time with any friction law that has a finite fracture energy. And then when and during this nucleation phase, the sliding patch should grow until it reaches a critical nucleation length. And at this point, the earthquake can propagate dynamically, allowing for the stress drop and the very large co-seismic slips, right? And so if we really want to understand when this main shock will occur, we first need to know where we are in the interseismic period. So what's the distance in terms of stress from the current stress state to the strength of the fault, right? And we also need to understand how long this nucleation process takes. And so to do this in a real case of induced seismicity, we have used rate and state friction law, a rate and state friction law, which from which we can derive the characteristic time of this nucleation process. So I won't go too much into the details of the rate and state friction law, but it basically tells you that the friction of the fault should depend directly on the rate of sliding and also on a characteristic time where the friction could increase when the fault is at rest, right? And so basically we can derive this parameter T sub A, which is the A sigma over tau dot, with A sigma being a frictional stress parameter and tau dot being the background loading rate. And by changing this characteristic time of the nucleation process, we can see here in panel C that we are indeed able to constrain how long it takes for an earthquake to nucleate. So the interesting thing about this rate and state friction law is that in 1994, Dietrich generalized rate and state friction to a population of fault to understand how seismicity rates change in response to stress changes. And so he used this for aftershock forecasting, but it has been since expanded to account for different types of loading on a population of faults. And so what you can see here in the top equation in blue are the changes in seismicity rates with respect to a background seismicity rates as a function of changes in Coulomb stress, delta S, and the parameters of the rate and state friction law. And so this is plotted here in panel E, where in panel A, sorry, where we can see the normalized seismicity rate versus time on a simulation for a given population of faults. And you can see that, again, if we change this characteristic time of the nucleation process, we will change the timing on when this population of faults reaches a constant seismicity rate in response to a ramp in stress in this example. So in black, you can see a ramp in stress in the second y-axis. The different colors represent different characteristic times of the nucleation process. And so you can see that really the response time of this population of folds is controlled by this parameter. When we stop loading our folds, this will go back down to a background seismicity rate, again, characterized by this nucleation time. Now, something that's important to notice here is that the Dietrich model accounted only for faults, a population of faults that was critically stressed. And in 2022, Jameson and colleagues relaxed this hypothesis with this new derivation that accounts for a strength excess, here delta S sub C, that will tell you that if faults are far from criticality, you need to increase the stress to a given point until they can start nucleating earthquakes. And so the response is shown here, where again, we have a period with no increase in seismicity, and then the seismicity is controlled by the characteristic time of the nucleation process. Okay, so what we did is that we used the case of Groningen as a natural setting, as an induced seismicity setting, where the amount of data that is available is really perfect to understand this characteristic time of the nucleation process. So there are a few things that make Groningen a perfect case example. First, here in panel A, you can see that is in a very quiet tectonic context. So this is the outline of the gas field in northeastern Netherlands. And you can see that most of the seismicity in the region is associated to the field. The earthquake catalog is really good because there's been a lot of interest in this case of induced seismicity. And the other two things that make this a perfect case is, as I am showing here in panel C, that we understand fairly well the mechanism for triggering inducing these earthquakes. So as we are extracting gas from this reservoir here in blue, we are driving offset compaction of different blocks of the reservoir that are offset by faults. And this offset compaction is increasing the Coulomb stresses near the reservoir. And this is what drives the earthquakes. And finally, the interesting thing about this reservoir is that first, the seismicity, as you can see here in panel B in red, started about 30 years after the start of the forcing of the system, right after the start of gas extraction. And the gas extraction operations had two very significant timescales. One that is a long-term timescale of the long-term extractions, but also a seasonal timescale of the forcing that you can see in blue. Where there's much more gas extracted in the winter to supply for Europe than in the summer. And so all these things make it such that we are, it's a perfect case example to understand the timing of the nucleation process. So here at Caltech, in the Center for Geomechanics and Mitigation of Geohazards, we have developed this workflow for earthquake forecasting that's called Flow to Quake. Where we have different blocks of different, say, physics-based models that connect with each other and that are calibrated using field data. So you can see we have first a reservoir flow model that takes injection or extraction data. It's calibrated on pressure measurements, and it outputs the spatiotemporal evolution of pressure changes. Then we input these pressure changes into a geomechanical model that uses a semi-analytical Green's functions approach. We calibrate the elastic properties of the reservoir using surface deformation observations. And this geomechanical model outputs Coulomb stress changes in and around the reservoir. And finally, we take these Coulomb stress changes and we put them into some seismicity model, which is the model for a population of faults by Jameson and colleagues that I showed you before. And these outputs seismicity rates. And we calibrate 3 or 4 parameters from this seismicity model using the observed seismicity. And so then with a calibrated workflow, we can hindcast and forecast seismicity rates. We can quantify the uncertainty associated to the whole process and so on. And so these are the results of our physical model. In panel A, you're seeing the evolution of pore pressure over time. So you can see that the pore pressure in the field drops by about 25 megapascals in total in about 60 years or so. And in panel B, you can see the development of the maximum Coulomb stress changes around the reservoir with time. And so if we take these Coulomb stress changes and we input them into our seismicity forecasting module, you can see that we do a great job at forecasting the rates of earthquakes that are plotted here in orange. Now, the interesting thing is that we're able to do that because we are taking into account significant seasonal stress variations with very large amplitudes that affect the seismicity rates. So what you can see here in panel A are the local changes in Coulomb stress at the points shown here in the map with the different colors, right? And you can see already the wiggles due to the seasonal changes in extraction. If we detrend these curves, you can see that the amplitude, the peak-to-peak amplitudes of the local Coulomb stress changes can reach about 20 kilopascals, which is fairly significant for our forecasting model. Now, in panel C, I am showing that the seismicity indeed responds seasonally to these seasonal Coulomb stress changes. So what you're seeing here is a random walk where we take a unit length step towards the occurrence of every earthquake in the seismicity catalog. And you can see that there is a clear drift with respect to the center of this plot, with more earthquakes occurring in March than the rest of the year. And so we are able to quantify the seasonality in seismicity using this technique. And so what I wanted to show you is that we conducted two different types of models. The blue ones, where we do take into account the seasonal stress changes and seismicity changes when we're calibrating the model. And the green ones, where we don't take into account that short time scale when we're calibrating the models. And you can see that after the training period, the blue models do a great job at forecasting the observed rates, but the green ones show a very large uncertainty in terms of the model calibration parameters. And so if we look at the parameter space of our seismicity model, you can see that the green models cover a much larger space of parameters than the blue ones. And so we are able to drastically reduce the uncertainty on our forecast using this secondary timescale. Now, and this is where I think I will finish. We are able to quantitatively assess the seasonality in the seismicity using these forecasting models. So what you can see here in panel C, D, and E are the same random walks from synthetic seismicity catalogs for our blue models, our green models, and also for a model where earthquake nucleation would be instantaneous. And so where there is no characteristic response time because this would be too short. And so you can see that our blue models calibrated using the seasonality reproduce extremely well the amplitude and the phase of the seasonality in the seismicity. The green models, when we are producing forward synthetic catalogs using the seasonality in the Coulomb stress changes, are not able to reproduce the seasonality in the seismicity catalog. And if we assume that earthquake nucleation was instantaneous, as for example is done in the seismogenic index models for earthquake forecasting, we can see that the phase and the amplitude of the seasonality is completely wrong. So even if we could match the long-term seismicity rates, the seasonal seismicity is completely wrong. And so this gives us insights into the characteristic response time of the earthquake nucleation process. So in the green models, we get values from about 1 to 100 years. In the blue models, we get values from about a month to 1 year. So we've already drastically constrained the nucleation time. And the yellow ones would be instantaneous nucleation. Now, if we didn't relax the hypothesis of faults being critically stressed, we would get values on the order of 100 to 10,000 years for this nucleation process, because the Dietrich model would absorb the lag between the start of the seismicity and the start of operations in a characteristic nucleation time, right? And so I think I've shown you that we can constrain laboratory-derived earthquake nucleation models, so we can constrain the parameters of rate and state friction using induced seismicity. This new method, by using different timescales for the calibration of our models, really drastically reduces the forecast uncertainty. And finally, we can tell to operators that it would be a very good idea to use multi-timescale operation strategies for early model calibrations and for having much reduced uncertainty on the seismicity forecasting models. So these are my conclusions, and I think I'm over time. So I think I will stay here and I will take any questions.
Excellent. Thanks so much, Mateo. This was wonderful. Lots of very interesting. Evidently, I have a lot of questions, but I will leave it to the audience first. Um, just reading off of the chat, we have from Peter Smealy. Thanks, Mateo. Need to make a lunch in DC. Nice work. Thank you. Nice work. From Wei, we have to sign off to attend another meeting. Thank you very much for sharing your interesting work. So thank you again. And we do have a question from Guo Tianyang at Stanford. Tian, did you want to unmute yourself, or did you want me to read the question out loud? No, he's here.
Yeah.
So. Oh, please.
Hey, Mateo. Very nice talk. So I'm also experimentalist. I'm curious about the lab part. So the first question is, how do you measure the transmissivity in the lab? In the page 13, on page 13, yeah.
Yeah, so the way we measure transmissivity in the lab, so you can see it in this plot. We have these folds, and we can inject or extract fluids from either the top or the bottom of the samples, of the folds, if you want. And so the way we did it in this study is that we imposed a small differential pressure between the top and the bottom of the samples, and we waited for a steady state flow to quantify the transmissivity. So you can find that in our publication in 2020 in JGR. There are other ways of measuring transmissivity. If you want to do it, for example, continuously, you could use oscillatory pressure changes at one of the ports and measure the changes in amplitude and phase of the pressures at the bottom. And you could also use pulse decay transmissivity measurements using the method of Brace. So I've done the three things. Here what we reported are steady state measurements of the flow using this differential pressure. But different methods are more applicable for different contexts depending on what you want to do.
Okay, so my second question is what fluid and what rock type did you use in the injection-induced seismicity lab test? Yeah.
Yeah. So we didn't do injection-induced seismicity lab tests per se. In this case, we did tectonic reactivation of faults at constant fluid pressure. So there is a slight difference with injection-induced seismicity cases because we're not injecting fluids to bring the faults to failure, but we're keeping the fluid pressure constant to understand the physics of how fluid pressure interacts with, say, what would be tectonic earthquakes. Now, this could also be applied with adaptations to fluid-induced seismicity. And for that case, we used westerly granite samples, which are representative of geothermal systems, I would say, but are also very suited for laboratory experiments because the very tiny grain sizes, very low anisotropy, and very high homogeneity make it such that between samples we can get very good reproducibility.
Okay, so what fluid do you use, water or?
Yes, in that case we used pure distilled water, but we've run some calculations on how this would work for example CO2 and with other types of fluids, and if we don't take into account the chemistry, we can really place ourselves in the pressure and temperature space where this heat buffering effect would be significant. And the absolute pressure and the temperature path would change depending on the fluid, but we are able to figure that out from equations of state of the fluid.
Okay, so you only do it at the room temperature. You do it at the higher temperature, for example, 100.
No, not for now. So we run some preliminary high temperature experiments at about 400 Celsius, and we saw a similar behavior, but the problem was that the reproducibility of experiments under a high pressure, high temperature was difficult to control.
Okay.
And we've published that uh, in World Geothermal Congress paper of 2021, actually. So I could share it.
Yeah, thank you so much.
Yeah.
Excellent. Other questions from the audience? Please feel free to unmute yourself or type it in the chat. We're a pretty small group, so hopefully not too scary or anything. While anyone types their question, I'll just start with one. In that study, I think it's the first one, where you're talking about the transmissivity not changing with shear displacement at high normal stresses. I'm wondering if you tested different roughnesses on that one and if that has any effect on that finding.
Yeah, we actually did. So here it is. So these are the results for different roughnesses. So basically here what we were doing is that we were customizing the sample's roughnesses, imposing grooves in our surfaces. So maybe I can show you the topography maps look like. So here in the bottom panel, in panel D, we have a surface where we impose the roughness only by with a sandpaper grit. But then in panels B, C, and E, we would impose it by milling the surfaces of our samples and leaving grooves, clear grooves on the surface of different amplitudes and different wavelengths. And we tested all these different things, and we get very different results in terms of, say, the absolute value of the transmissivity, but the trends with increasing shear displacement remain. So you can see here are for the different roughnesses, the different colors. Then the lighter colors are lower stresses and the darker colors are higher stresses. And you can always see that the transmissivity decreases and there's no real increase of the transmissivity. Yeah.
Okay, very cool. This actually answered the other question about the roughness because I've also been playing with using 3D printing and random fields to generate artificial roughness. But the problem with us is we have to cast it with, for example, concrete, these artificial surfaces. Where you get to work with these. I guess this is still granite in situ, which is much nicer in this respect. Okay.
Something I could share with you is that we developed a numerical model where we we actually and you can find this in the paper. I didn't go too much into the details, but what we do in this model is that we measure the statistical properties of our surfaces. We generate numerical rough surfaces. Then we put them in contact using a contact mechanic algorithm that calculates the elastoplastic interactions between the different contacts. And from there we get an aperture field. I don't know if you're familiar with the Polonsky and Kier algorithm, but that's the one we use. And then we simulate the flow through that aperture field. And so what you can see here in panel C is the simulated flow. And actually, when we compare our numerical values to the experimental values, we get a very tiny error. So this is what you're seeing here in panel B. We have the numerical transmissivity, the experimental transmissivity. And something we see is that if we simulate the surfaces not being mated, then we overestimate the experimental transmissivity. But if we simulate the surfaces being fully mated, then we get a one-to-one slope within a very tiny error of about 2.5. And so this numerical model works really well, and then we can explore very different ranges of transmissivity using this numerical model. I can show you here. Sorry, there you go.
Hmm.
So then we explore, the different statistical properties of the surfaces, and we understood that there's two parameters that control the fluid flow through these fractures. It's not the Hurst exponent. It's not the roll-off wave vector. It's really just the RMS and the wavelength of these macroscopic grooves. So I think it's an interesting, it's a cool approach
Yeah.
because we're able to calibrate that model without any fitting parameters. It's just material
Yeah.
property
Yeah.
and the properties of the rough surfaces. So
Right.
yeah, it's all in that
Oh,
paper.
that's super cool. Yeah, this is really cool. Okay, excellent. No other questions have popped up in the chat. So with that said,
I got
then,
one,
oh, sorry.
if you wouldn't mind.
Please
Yeah.
go ahead.
Okay, is my voice clear?
Yes.
Yes.
Okay, thank you for the great presentation. I have a question to ask. I was just wondering if you have considered the effect of geochemistry in your experiments, because as we all know, like in the process of carbon sequestration, if CO2 is injected underground, it may result in salt precipitation, which can change porosity and permeability of pore throats. I was just wondering if you have considered these kind of effects in the experiments or not.
Yeah, that's a great question, and that's something that I will. For now, I haven't done that. For now, I've been focusing on really the mechanical and hydraulic transport coupling, right? Just in that sense. But of course, for real reservoirs, you definitely need to control to understand the geochemistry. And so that's part of what I'll start doing now in that I'm moving to Virginia Tech, is really to incorporate hydromechanical chemical coupling processes. Um,
Mm.
so I think there's a lot still to be understood in terms of hydromechanical couplings. But of course, if you want to go back to real reservoirs and to understand what's happening there, you would need the chemistry. Now, something we don't really know is the different time scales and the different length scales over which these processes operate, and it would be very interesting to know uh, if some of these processes can be depreciated in terms of physics-based modeling, um, in order to simplify the problem. So that's what we've been doing for example, for the Groningen case and for this induced seismicity at reservoir scale. We've been trying to keep the minimal physics needed to explain the data. And that has allowed
Yeah.
us much faster computations and models that can really cover the range of uncertainty that we want to quantify and so on. And so again, my approach is really to try to understand, the minimum physics that are needed to understand the process, rather than start very complex and have too many free parameters. So that's also why I
Oh
have
yeah.
chemistry, but I am sure it's going to be important. Yeah.
Yeah. Thank you. Thank you very much.
Excellent. So yeah, absolutely. Thanks so much, Mateo, for the presentation. Lots to think about. And with that, and congrats on your new position.
Thank you. Thank you for the invitation. And yeah, drop me an email if you want to discuss anything.